Hi everyone, we're on text and test 4 here, page 406. We're looking at the shapes of distributions, okay? And this is a type of a language and a way of talking about data that you need to develop. It can feel a little bit woolly at first, but you do need to be able to speak about the shape that a distribution has. I'll start off with D over here, which is a symmetric distribution. A symmetric distribution is lovely, easy to talk about. You can see the lowest group and the highest group are about the same size. You've got an axis of symmetry you can draw down the middle. We talk about symmetric distributions a lot in theory and practice. When they come up, they're normally not that perfectly tidy from real data sets, but very often they're a very good approximation of a lot of real data sets. All of these other ones could be described as being skewed in some way, or non-symmetric or non-uniform, or you'll hear different words, but skew, I suppose, is probably the most common one you'll hear. Now, this is what's called a bell curve or a normal distribution. Okay, a normal distribution is really the one that we're going to call it for the most part. This shape here, okay? We generalize the shape with this type of a curve. But I want you to remember, anytime you see a curve like that, that really what you're looking at is a histogram where all of the classes or groups are very, very narrow. And what we're looking at is the shape that that histogram takes, okay? Normal distributions like this, you'll see this occur really often if you take large data sets from people and you measure things to do with biology, things like their height. You'll get, for 1,000 people, you'll find a certain number of small people and about the same number of very tall people, most people clustered here around the middle. And we're going to be describing the normal distribution in the next chapter a huge amount. So, get used to it now. You're going to hear it for things like height, weight, if it's lifespans, if you're talking about the growth of plants, maybe it's the height that plants grow to, or the weights that fruits on plants are produced, things like that. It comes up an awful lot in science, and it'll more than likely in whatever third level course you do, you'll have to do statistics in something at some stage, and you'll see the normal distribution. This idea of skew, I'm going to include a little bit more when we actually meet questions. Okay, but it's this idea that you have essentially a normal distribution, and then the tail, this bit, has been pulled up to the right. That is, more data has been entered. So in this example, if this was heights, this is a population of people that has kind of an almost normal distribution of heights, but then up here there's a few extra tall people have been added into the population, say. Okay, so the tail has been moved to the right, and that's called a positive skew. And the effect of adding in, if you like, those extra tall people is that the mean value, the average, or when you add all the heights together and divide by the number of people, you get a higher value. Okay, the mode, the most common height, that stays exactly where it is. That doesn't change. The median, because you now have a few extra tall people, that's going to be dragged up a little bit by comparison with the mode. Okay, in a normal distribution, mean, mode, median are all the same. They're all that middle value. A normal distribution, the center, no matter how you measure it, you'll always get the same answer. A negative skew is same type of thing, except now if you were including some very short people, say, assuming this is data for height, well, all those extra short people are going to drag down the mean height. The modal height, the most common height, won't change at all. And again, your median is going to drop a little bit, okay? So that's a negative skew, where you've kind of added in extra data on the negative end, as it were, of your normal distribution. So they're talking about this in comparison with the normal distribution. Uniform distribution just means every category has the exact same number of elements. Modes, you'll see, so you'll talk about this is the mode of a distribution, is the highest point, but sometimes you'll have two highest points, like here or like here. That's called a bimodal distribution. And what is going to feature quite a lot in this exercise is discussions of the standard deviation. Okay, remember, that's how far am I spread from the average. So in both of these examples here, you've got a mean of 3.5, right? If you were to say, well, what is the standard deviation here? What's my average distance from the mean? Okay, well, an awful lot of your data is very close to the mean in this example here. Okay, all of this data here, that's 6 and 9 and another 7, was that 22 people in this survey are very close to 3.5, but over here only 4 and another 3, 7, and maybe another 6, so only 13 people are close to 3.5. Most people in this case are very far away from the mean. So even though these two data sets look like the range is probably the same for both of them, it's between 1 and 7. Okay, these are the values here that we're looking at. Even though the range will be the same, the standard deviation is going to be an awful lot higher in this second diagram B here, because more data is further from the mean. Okay, so I think we'll jump in and look at some questions now. We'll start looking at three distributions. Which of these distributions is symmetric? I think it's reasonably obvious that C there is the only example that is symmetric, that you could draw a kind of a line of symmetry down here if you wanted to and fold it in half. So that's symmetric. That's what that means. Which distribution is positively skewed? That means you've got, I suppose, more data on the positive end, or you've got a buildup of data, or you've got a tail on the positive end. So if we were to try and fit a normal curve, I think A here, you can see it have a tail on the positive end, whereas B, if you're trying to fit a normal curve to B, you can see the tail is on the negative end. So A is positively skewed, B is negatively skewed. Which distribution is most likely to represent the weights of international rugby players? Now, if you look here, you've got a lot of weights that are low weights and not so many that are high. That's probably not going to be rugby players. If you look at option A, you've got a lot of very high weights, and even the low weights, yeah, I suppose everyone's heavy, but you've got a few people who are really, really exceptionally heavy up here to the right. Is that fair? That's not fair. Apologies for that. Yeah, you've got a lot of people here who are at low weights, excuse me, and not so many who are at high weights. So sorry about that. B is going to represent your rugby players. Very small number of people who are at low weight compared to the population. The most common weight is quite high, and you've got a few people who are very, very heavy up here. Sorry about that. The weights of international rugby players. Which distribution best represents the intelligence quota or the IQ of a large number of second level students? Well, IQ, similar to height and weight, tends to be normally distributed. So that's going to be this symmetric distribution that we see here. Probably the best measure of IQ. Question 5 is a nice one about standard deviation. You've got two distributions, A and B. Why is the data in B why does it have a greater standard deviation than the data in A? Well, if you look here, our average value is 2.5 in this first one. So 2.5, a lot of our data is clustered around that 2.5 in A. Excuse me. Whereas in B, if you look at that 2.5, not so much. The data is further away, these 6 people here, and these 3 people here that are between 4 and 5. A lot of that data is further away from the mean value compared to over here, far away from the mean value, you've only got a small number of people. So because more data is further from the mean, you're going to see a larger standard deviation. Okay, and I think all the questions that follow are along a similar line. So what I'll ask you to do is, as well as having questions 3 and 5 done into your copy, can you also please do questions 6 and 7 into your copy as well, okay, which all follow this first instruction here. Is the standard deviation larger or smaller for each set? Okay, we'll leave it there. See you tomorrow.